Thank you everyone from the QWorld Quantum Summer School and in general from QWorld applicants as well to our QWebinar. This is, I believe, our 14th webinar. And very graciously, Omar Fawzi has accepted our invitation to speak. And he'll be talking about quantum error correction. Before we begin, please note that we want to ensure that there's no harassment. Everyone maintains kind of a nice environment for everyone to discuss. Please do not record this session. We will record the sessions ourselves and make the recordings available on YouTube afterwards. And if you want to communicate in terms of asking any questions from the speaker, either just put down your questions on the Zoom chat or put a comment in the YouTube video comment section. I'll be collecting those questions and then we'll kind of take all those questions individually and then in Q&A. Right, so there are minimum interruptions in the middle of the talk. If it seems like there's a very pertinent question during the middle of the talk, then I'll kind of review those questions and interrupt accordingly. Does that sound reasonable? Right. Let me introduce Dr. Omar Fawzi, Professor Omar Fawzi, who's the speaker today. Omar is currently research director at Inria, Lyon. He received his PhD from McGill, and his research interests are in quantum information theory and quantum cryptography. And today he will speak to us about quantum error correction. And so with that, I'll give it to Omar. Stop sharing my video. Don't worry, you could go ahead. Yeah, you've got your screen. Omar, we don't have audio. Mute.
Now you can hear me?
Yes, we can hear you.
Yes.
You're good to go.
Just check that the slides are okay. Sometimes that's okay. Okay, good, excellent. So thanks for the invitation. So yeah, I'm going to be talking about quantum error correction, and this is mostly going to be an introduction to quantum error correction. And at the end, I'll try to give you a little bit of an overview of some of the recent progress and some of the challenges in this area.
Omar, does your screen show the slides? So we don't see the slide in our show.
Yeah, so that's why I was. So you don't see the slides?
No, you see a black.
I think actually. So I will not do a full screen.
Okay.
Mode.
Yeah.
Maybe that would be. Yeah. Okay. Okay. So yes. So as I said, so I'll be talking about quantum error correction. So first, a bit of motivation. So as you probably all know, so quantum technologies have a huge potential in terms of applications for computation, cryptography, communication. But the reason that many of these applications, we don't have them right now, is that quantum information is very fragile. And so it is very difficult to prepare quantum states. It is very difficult to run these quantum algorithms in such a way that they're not affected by noise. Okay, and so yeah, so given this state of affairs of how the quantum hardware is noisy, so there are several questions one can ask, is to say that just so what are the interesting circuits that I can just run with this hardware that I have? Okay, so for example, if the circuit is small enough, then and if I have, for example, that the error probability is 1/1000, then if the number of components of the circuit is less than 1000, then I don't expect there to be an error. So I can look at these kinds of applications. Or the other thing, more long-term, is to say that what kind of mechanisms we can construct in order to realize reliable computation, even if the individual components that I'm using are noisy. Okay, and this is what I'm going to be focusing on in this lecture. The second point. Okay, so first, in order to motivate quantum error correction, I will talk about fault-tolerant quantum computation. The objective here is, so yeah, before getting into fault-tolerant quantum computation, let me just try to convince you that there is a difficulty. So first, and this difficulty has to do with the propagation of errors. Okay, so let's see that with a very simple circuit. So let's consider this simple circuit on 4 qubits. Okay, so assume they're all initialized in the 0 state. And I apply a CNOT gate between the first and the second qubit, and then the second and the third qubit, and then the third and the fourth qubit. Okay, and then I perform a measurement. Okay, so if I do this ideal circuit, then you see that the outcome is going to be just all zeros with probability 1. Okay, but now imagine that I try to run this circuit on an actual quantum computer, which might have some errors. And imagine that for some reason, there was an error that occurred on the first qubit. And the effect of this error was that it applied a NOT gate on the first qubit at the beginning. Okay, so as you see, it's easy to see here that the effect of this error is that this is going to be a 1. And so now this is going to flip to, the second qubit is going to flip to 1. The third qubit is going to flip to 1 as well, etc. Okay, so, and then if I perform a measurement of these 4 qubits, the outcome I will get is all 1s, right? Instead of all 0s. Okay, so this was just to convince you that if you try to use the ideal circuit that you designed on a piece of paper on an actual quantum hardware, and that if this hardware is prone to noise, then it could be that a single error somewhere leads to a completely wrong answer. Right? And so, yeah, so this is the difficulty of error propagation. And so the point of fault tolerance is to try to keep the errors under control. Okay? And so the challenge here, the question is it possible to keep the errors under control in a way that they don't spread in this fashion that I showed in this small example. And so we know since the beginnings of quantum computing that this is in principle possible by the famous quantum fault tolerance theorem, which says the following. So it says that I can transform any ideal circuit C. So C is the circuit that I would like to run. For example, think of C as Shor's algorithm. And I can transform the circuit C, okay, into another circuit C prime, okay, which will typically be larger, right? So instead of using M qubits, it will use M prime qubit, which is a bit larger than M. And instead of using T gates, it will use slightly more gates than C. Okay, but the important thing is that so C prime will give me the same answer as C. Okay, so for example, if I'm running factoring, it will give me a factor with high probability, and this will be even if the components of C prime are noisy. Okay, so even if C prime has some noise in it, of course below some noise rate, okay, below some noise rate P is 0, then C prime will give me the right output. Okay, so so I won't talk explicitly about quantum fault tolerance today, but I will talk about a very important ingredient that enters in proving this fault tolerance theorem, which is quantum error correcting codes. So yeah, a brief outline of this talk. So the first part, it's going to be an introductory to quantum error correcting codes, and I'm going to show you that quantum error correcting codes exist, okay? Which might be not very intuitive at first, but they do exist. And the second part is going to be about general constructions, and I'm going to try to briefly define some of the famous codes, like the surface codes. And the last part is going to be about a more general family called so-called LDPC quantum codes. Okay, so let me start with the beginning. So about error correcting codes. Okay, so the objective of classical or quantum error correcting codes is to store an information of interest, which I'm going to be calling data here, or logical information in this talk. And to store it in a way that makes it robust to errors. Okay, and the main idea of error correcting codes is to spread this data or this information of interest across multiple systems. Okay, and the reason is that typically our error models will be local. And so if we spread the data across multiple systems, then this will ensure that even if we have errors locally, then globally we can still recover our data. Okay, so let's start with the simplest classical example. So assume that my data that I would like to store is just a bit b, okay? Also call it a logical bit. So the simplest error correcting code is the repetition code, which is just to say that I take my, my data b and I encode it in 3 bits. So these are going to be called, I'm going to call these 3 bits the physical bits. These are the ones that I'm going to really store on my physical machine. And so I'm going to map the bit 0, the data bit 0, or the logical bit 0, to the physical bits 0, 0, 0. Okay, and similarly, I'm going to map the bit 1 to the physical state 1, 1, 1. Okay, so this is a very natural choice of code. So before talking about the correction capabilities of this mapping, it's important to define what the error model that we consider is. Okay, so here I'm going to consider a simple error model. So, and I'm going to consider only 4 possible errors, right? So, so the first possible error is just that there's no error at all. Okay, so my 3 physical bits are unaffected at all. And the other possible errors are the fact that the first bit gets flipped. So the first bit gets flipped from 0 to 1, for example. So it's possible that the first bit gets flipped, the second or the third gets flipped. Okay, so I call it X because X is the NOT gate, at least in quantum notation. So this will make it simpler because the quantum notation will be the same. Okay, so this is assume that I can only have an error on 1 of the bits. Okay, so I will never have an error on 2 of the bits simultaneously. Okay. So note that this is not necessarily very realistic, but it's a good first order approximation. As typically, if we put a probabilistic model on this and say that we have an error with probability p, then the probability that I have an error at 2 places goes like p squared. Okay, and so if p is small enough, we can neglect this term. Okay, so now this is the well-defined error model that I have. And so the claim, the error correction claim that I make here is that it's possible to recover the data, which I call B, from the corrupted physical bits. Okay, so imagine Y is obtained by the encoding of B plus some error, okay, where the error lives exactly in this error model. And the claim is that for any error in this error that satisfies this error model, I can recover B. Okay, and here I guess it's very simple to see, and the way to recover B is just I do a majority vote of Y1, Y2, Y3. Okay, so I take my 3 physical bits and I take a majority of them, and this will give me B. For example, if I have 0, 0, 0, and if I have that the third bit gets flipped, so I have 0, 0, 1. If I take the majority, I get 0. So this is correct. Okay, so this is a very simple code. So now let's try to do this in the quantum setting. Okay, so let's try to construct a quantum error correcting code that allows us to correct errors that happen, let's say, on 1 of the physical qubits. Okay, so if you try to do this generalization, it might seem quite difficult at first. And there are several reasons for this. Is that first, so you see here what I did is I just repeated the logical data. Okay, so 3 times. Okay, so maybe the most straightforward way you could try to generalize this is say that I try to take the state psi and copy it 3 times. Okay, but as you probably all know, this is not possible by the no-clouding theorem. Right? So such an operation is not physical. So I cannot do this. So this is one first difficulty. Another difficulty is the fact that the correction procedure will, in general, can affect the data itself. Okay, so for example, here, if I look at this algorithm, I have to look into the first bit, the first physical bit, the second physical bit, and the third physical bit. Now, if I try to do these measurements, if I try to measure something about the first qubit, then this will affect the data that is stored. So this might be problematic. This is a second issue. Like a third difficulty, which you can see is that in the quantum case, there are much more errors, right? So here, I just have the possibility of, so the 0 will go to a 1, the 1 will go to a 0, and that's it, right? But in the quantum case, I can have, let's say, an arbitrary rotation of the first qubit, let's say. And so this this leads to difficulty. Okay, but it actually turns out that one can overcome all of these difficulties, and quantum codes do exist. Okay, so let's start introducing this by looking at the quantum repetition code. Okay, so this will be like a direct analog to the repetition code we saw before. And so I will do the following. So note that here now I have quantum information. So I would like to encode a quantum state, psi, which is a qubit. And so my repetition code will encode this qubit into 3 qubits. And this is the way it will work. So in direct analogy to the classical case, I will map the state ket0 to 0, tensor 0, tensor 0, which I'll just denote by 0, 0, 0. Okay. Similarly, I will store the state ket1 by 1, 1, 1. Okay. So first, notice that so by linearity, this defines the encoding for any possible quantum state, alpha 0 plus beta 1. So if I have alpha 0 plus beta 1, I will this will get stored as alpha 0, 0, 0 plus beta 1, 1, 1. Okay, and notice that this is actually, I'm not cloning here, because this state is different from the state alpha 0 plus beta 1 tensored 3 times. Okay, these are not the same state. Okay, so this is a well-defined encoding, and this is what I call the quantum repetition code. And so again, before getting into the error correction statement, let me tell you what the error model is. And I'll start with a very simple error model with a very limited set of errors, and assume that, as in the classical case, I will assume that there are only 4 possible errors to start. Okay, so again, I will be no error, and xi is the physical bit number I gets flipped. Okay, and here x I have, so x I can represent it as a unitary here, which just flips 0 and 1. Okay, so just an example to make sure the notation is okay. So if I apply this encoding on the state 0 plus 1, then I get the physical state is 0, 0, 0 plus 1, 1, 1. Okay. And now if I have an error that affects the first qubit, then I get the state 1, 0, 0 plus 0, 1, 1. Good. Okay, so now let me make the error correction claim, which is that now if I'm given, so if I encode my state psi, my unknown state psi using this code, and then this is affected by an error in this that lives in this error model, then I have a procedure, like a physical procedure, that allows me to get back the encoded state. Okay, the encoded correct state. Okay, so more formally, what I mean by this is that if I consider this encoded state, psi encoded using this repetition code, and then this is affected by some error E, which lives in my error model script E here. Then there is a recovery procedure, which we can describe by a quantum circuit, that recovers exactly this correctly encoded physical state. Okay, of course, this has to work for any error and for any state, for any choice of data state psi. Okay, so this is clear. So let me now describe how we actually do this. I will try to describe to you what is this recovery procedure, R. And so perhaps let me maybe just focus on perhaps one of the main ideas here is that in this recovery procedure, instead of trying to determine what the data psi is, what I try to determine is what the state, instead of trying to determine what the state psi is, what the data state psi is, I try to determine what the error is, E. Okay, so my objective is to see what is the error. And the error procedure will have 3 steps, as I described here. So the first step is going to be that we're going to perform some measurement, okay, which I'll describe next, which was going to give me 2 bits, S1 and S2, which I'm going to call the syndrome of the error. Okay, and then from these syndrome bits, S1 and S2, I'm going to infer some error E in my error model. Okay, from these syndrome bits, S1 and S2. Notice that actually this step is a completely classical step, okay, this classical algorithm. And then what I will do is, given that I know what the error is, I will actually undo this error. Okay, so for example, if the error was a flip of the first qubit, then I just apply it again so that this error is flipped back. Okay, so so this is the general idea of the error correction procedure. Let me say more precisely how it works. Okay, and in particular, the main step is this first step, which is to measure the syndromes, S1, S2. Okay, so notice that the thing to notice is that in this repetition code, you see if I'm in an encoded state, right? So any state of the form alpha 00 plus beta 11, if I look at the first and the second bit, they have to be the same, right? They have to have the same value, either 00 or 11. Okay, and this is exactly what I will measure. So my syndrome will be, I will measure whether the bit 0 is equal to bit 1. The bit 1, the first physical bit is equal to the second physical bit. Okay, I will not measure what the first physical bit is. I will measure whether the first physical bit is equal to the second physical bit. Okay, and so the way to do that is to say that, for example, is to apply a controlled knot with a new ancilla qubit here that I prepare in the state 0, and I do a C knot between, let's say, the first qubit and the second qubit. Okay, so you see that what I will have here is a bit that will tell me whether it will be 0 if bit 0 is equal to qubit 0 is equal to qubit 1, or it will be 1 if they're different. Okay. And then I perform a measurement. This will give me the bit S1. And I do the same thing by checking that the qubit 2 and the qubit 3 have the same value. Okay. And I do it with basically the same circuit, and I perform a measurement here, S2. Okay, so notice that if there was no error at all that happened, right? So if my initial state, if the state that I'm measuring is of this form, alpha 00 plus beta 11, then actually I will always get S1 equals 0 and S2 equals 0. Right? You can check this. It's simple. I will always get 0, 0. Okay? But if there is an error, I can get that the syndrome will be different from 0, 0. Okay, and so in particular, now let me try to describe to you what the second step is. So where I have the syndrome bits S1 and S2, right? And I want to infer from that what was the error that happened. So here it's easy to see that if S1 and S2 were both 0, then I conclude that actually no error happened. If on the other hand I see, for example, 0, 1. Okay, so the first syndrome bit is 0 and the second is 1. Then it means that the second and the third qubit are different. Okay, but the first and the second qubit are equal. So this tells me that actually the error happened on the third qubit, right? Okay, so I will infer that the error that happened is on the third qubit. Okay, and similarly, if I have 1, 0, then this tells me that the error is x1, and if I have 1, 1. If I see S1 equals to 1 and S2 equals to 1, then I infer that the error that happens is in X2. Okay, so, and then once I have this, I just undo this error E. Okay, so if, and this is my recovery procedure. Okay, so perform the measurement, do this classical algorithm where I map the syndromes to an error, and then just undo the error. Okay, and then if you check just these calculations, you'll see that this is satisfied. Like the claim, this property is satisfied. Okay, so this is nice. This is our first quantum error correcting code. So it's nice, but the problem is that it corrects only a very limited set of errors, right? Only just bit flip errors on bits 1, 2, or 3. So what happens for more general errors? Okay, so let's start with like a specific kind of error here, which is an example of which is this. So on the first physical qubit, I applied this unitary. Okay, the exact details of this unitary don't matter so much. The important thing is that this unitary can be written as a linear combination of identity and x. And there should be a parenthesis here. But, yes. Okay, and so let's see that actually for this error, because it's a linear combination of errors that I can correct, then the exact same procedure as before will also correct this error. Okay, and so this is relatively easy to see. So let me place myself right before these measurements, this syndrome measurement here, after applying these C-notes, but right before these measurements. And so in this case, my state by linearity will be the state where I have no error at all, right? Because remember, E is a linear combination of I and X1. So again, my output state will also be a linear combination of the true state to which I apply identity, which is just this one, and the true state to which I apply X1. Okay. And notice that here, because so here I have no error at all, so naturally these two syndrome bits will be in the state 0, 0. And here I have an error on the first qubit, okay? And so my syndrome bits, my syndrome now qubits still, I didn't measure them yet, are in the state 1, 0. Okay, so now if I measure now these registers, this one or this one, then what I will have is actually that the state will collapse to one of these two states. Okay, so with probability half, I will get the outcome that the syndrome bits are 0, 0, and the corresponding post-measurement state will be this one. But on the other hand, if I get S1, S2 is equal to 1, 0, then my post-measurement state will just be this part of the state. Okay. And of course, you see that, so if S1, S2 is equal to 0, 0, then I infer that the error was identity and I don't do anything. If, on the other hand, S1, S2 is equal to 1, 0, then what I will infer as an error is X1. And so after I undo X1, I will have again the correct state. Okay, so you see that here, the exact same procedure will work. And you see what happens here is that I'm basically projecting the error to either the identity error or the X1 error. Okay, so by performing the syndrome measurement, I collapse the error, if you want, into one of these two errors. And then I correct correspondingly. Okay, and so you see here that this is a quite general fact, is that if I have a procedure that corrects both E and F, then it also corrects any linear combinations of them. Okay, so that's good. So we can correct a little bit more. So not only identity and X1, but even linear combinations of them. But of course, so if I take linear combinations of these matrices, I don't get all the possible errors. And in particular, one important error that is missing is what is called phase error. So like applying a Z gate on, let's say, the first qubit, this is not going to be corrected at all by this procedure. Okay, so the question is, how do we correct it? So let me briefly sketch how Shor did this in his 9-qubit code. By the way, this was the first example of a quantum error correcting code. It was discovered by Shor shortly after his factoring algorithm. And so the idea is as follows, is that if I take now, remember my interest now is trying to deal with Z errors. Okay, so and the idea is that if I define this small variant of this repetition code that I defined in the previous slides, by instead of encoding 0 in 0, 0, 0, I will encode 0 in the state plus, plus, plus. Okay. So and plus is just the state 0 plus 1. Okay, and minus is the state 0 minus 1. And you will see here that actually this code, it can correct all the Z errors, right? Because what Z does is it flips a plus to a minus. Okay. So X flipped a 0 to 1, Z flips a plus to a minus. So yeah, so with exactly the same proof, you see that this code, this Q bar rep3, it corrects all the Z errors on a single qubit. Okay, so now I have two codes, one that corrects X errors and the other that corrects Z errors. I would want a single code that corrects all of them, not separate codes. And but there's a nice trick you can use for that, is concatenation. Relatively simple and natural, is to say that actually I first use, for example, this one, the Q bar rep. I get 3 physical qubits. Then I take each one of these physical qubits and I encode it in the quantum repetition code I defined before. Okay, so in total I get 9 physical qubits. Okay, so that's why it's a 9-qubit code. And it turns out that you can show that this code can correct any error on a single physical qubit. So any error on one of these 9 qubits can be corrected. Okay, and I won't prove this, but an important fact that is used here is that I can correct X errors, and I can also correct Z errors on any single physical qubit. And so as a consequence, I can also correct X times Z errors, okay, which are also called Y, up to this I factor. And so these form what is called the Pauli operators. And these Pauli operators happen to span the set of all 2x2 matrices. Okay, so yeah, so if I take I, X, Z, and Y together, they span the set of all 2x2 matrices, so I can correct actually any error. Okay, so this is the idea, and so let me, before moving to the second part, let me briefly summarize what we have seen. Is that so? The first thing is that there exists an encoding, is the existence of a code, so that encodes a logical qubit into 9 physical qubits in such a way that I can recover the encoded state from the state to which I applied an error. And this error can be arbitrary as long as it acts on a single physical qubit. Okay, and in order to achieve that, there were some ideas, interesting ideas, is that you focused on measuring the error and not the data. And the second idea is actually that quantum errors are discrete, in the sense that if you have a quantum error correcting code that can correct X errors and Z errors, then it can correct all errors actually. Okay, so you only need to care about X errors and Z errors. Yeah, so just I guess this is convincing that this reduces errors, but maybe it's a bit more convincing with a probabilistic model. So imagine that now I have a probabilistic model for errors, and assume that each qubit has an error with some probability p, some small probability p. Okay. So if I do no encoding at all, if I leave just my qubit as is, then the data that I have will have error with a probability p. Okay. Whereas if I use this encoding, if I use this 9-qubit encoding, okay, and I assume that on these 9 qubits I also have the same probability of error p, then you see here that the probability that there is a logical problem, that there is an error that happens to the data itself, there has to be at least an error on 2 physical qubits, because if there is an error on 1 physical qubit, I can correct it. But if there is an error on 2 or more physical qubits, then It's not clear whether I can correct it. And so you see here that the error probability of on the logical qubit is of order p squared, right? So because I have to have an error on at least 2 qubits, right? So that's why it's quadratic in p. And so you see that if p is small enough, then this big O of p square will be can be significantly smaller than the error rate I had if I didn't do error correction. Okay, so that's it for the first part. Let me move on to the second part, which is about giving more general constructions of quantum codes, right? So now I would like quantum codes that can correct more than just one error, right? Because typically we have large blocks and we would like to be able to correct more than just one error. And so I will try to give you an idea of how one can construct such codes. And so before getting into it, just a brief technical remark is that so far the way I have defined the code is by an encoding function, by telling you I encode the bit 0 into C of 0, etc. But for the rest of the talk, actually, the only important thing is going to be the range of this encoding function. Okay, so what are all the sets of encodings of valid physical states? Okay, so that's why I will be talking about a classical code as a subset of 0, 1 to the n. You should just see it as the range of this function C. Okay, and similarly, in quantum code is a subspace of the set of the space of n qubits. Okay, good. So so the natural question that we can ask here, given what we saw before, is we saw that basically a quantum code, in order to construct a quantum code, I need to be able to handle two kinds of errors, and they play a symmetric role, the x errors and the z errors. So the natural question is it possible to take a classical code for x errors and a classical code for z errors and combine them in a way to get a quantum code that can correct both of them? And it turns out this is possible. And this is this famous CSS construction, which works as follows. So I start with two classical codes. So they have to be specific codes. They have to be linear codes. So in the sense that this subset that represents the code has to be a linear subspace of f2 to the n. Okay, and the way I'm going to represent the subspace is as the kernel of some matrix hx, which is also called parity-check matrix. Okay. So imagine I have a matrix, an mx by n matrix, and an mz by n matrix, which we can see as representing classical codes. Okay, so this will not work for any such matrices, hx and hz. There is an important condition, namely that I have to have that the rows of x and z are orthogonal. Okay, and here everything is over f2. Okay, so I have to have that hx and hz are orthogonal. Then I can take these two matrices and use it to define a quantum code, okay, which will be a subspace of the set of n qubits, and it will encode n minus mx minus mz qubits. Okay, so it's not very complicated, but I won't tell you exactly how this Q is constructed. Yes, so yeah, let me not get into this. And so the quantum code Q inherits some of the properties of hx and hz. Okay, so namely, for example, if hx and hz can correct t errors, for example, then the quantum code will be able to correct arbitrary errors on t qubits. Okay, so let's see a simple example of that. So I can take this matrix. So it's a 3 by 7 matrix, which is given by these. And I take, actually, in this case, it's a special case where hx and hz are exactly the same matrix. Okay, so let's look at what are the parameters of the corresponding quantum code here. Okay, so first, the number of columns is 7. So n is 7 in this notation. The number of physical qubits is 7. Okay, another thing that I have to check here is that the rows of hx and hz are orthogonal over f2. Okay, so how do I check this? So here hx and hz are the same. So if I take the inner product, let's say of this first row with itself, okay, you see that I have an even number of ones, so it gives me 0. Okay, so it gives me 0 mod 2. And similarly, if I try to take the inner product between the first row and the second row, you see that I only have these 2 entries in common. So I have 2, and this is 0 mod 2. Okay. And so this is valid. This condition that the rows of hx and hz are orthogonal is satisfied by these matrices. And so I do get a valid quantum code. And how many qubits can it store? I have to use this formula here. So it's n, the total number of qubits, minus basically the number of constraints that is given by the matrix hx, minus mz, which is the number of constraints, which is given by hz. Okay, so here it's 3. So I get 7 minus 3 minus 3, which gives me 1 qubit. Okay, so I can store 1 qubit, and it's possible to show that it can correct exactly 1 error. Again, this is simple to see just by seeing that classically this error correcting code can correct 1 error. This is a very famous code. It's called the Hamming code, and so it's simple to see that it can correct an arbitrary error on a single bit. Okay, so that's it for this this quantum Hamming code. Now let me get to another important family of codes, which are called these surface codes. So yeah, first this is a family. There's multiple variants of it. So I'll take a specific one here, and this is really probably the leading candidate so far, at least for to be used in quantum computers, because of the many advantages. I will mention a few of them in the next slide. Okay, so let me now tell you how this code is defined. Okay, so the physical qubits are represented by edges of this grid, right? So I draw this grid, and it has these edges, and each one of these edges is a physical qubit. Okay, so this has a bit more than 100 physical qubits, one for each one of these edges. Okay, so n is given by this. And so now I have to tell you what are the 2 matrices, hx and hz. So let's start with hz. So how is hz defined? I take each one of the squares of this grid. Okay, so I take a square in this grid, and I look at the neighboring edges. Okay, and I put, so, and I will have 1 row for each one of these squares. Okay, and for this corresponding row, I will put a 1 in the neighboring edges. Okay, so for example, for this square, let's say, I will put a 1 for each one of these neighboring edges. Okay, so I will do this for all of the squares. So notice that at the border, things are a bit special in the sense that I will only take the 3 neighboring edges instead of 4. Okay, so the rows of hz will have either 4 1s or 3 1s, depending on whether I'm inside or in the border. Okay, and hx is very similar. Hx, except that instead of looking at the squares, I look at the vertices, right? So here I take each one of the vertices of this grid, and I look at the neighboring edges, and I put a corresponding 1. Okay, so good. So the first thing to check here is that we satisfy this orthogonality condition, and the reason is that if I look at an element in hx, a row of hx and hz, then you see that they will overlap in either 0 edges or exactly 2 edges. Okay, and so this will ensure that that we have this orthogonality condition. Okay, so now what about the parameters of this code? If you count the number of squares that we have in this grid, then it happens to be L squared plus L minus 1 squared, where L is the number of edges that I have at this site. Okay, and so again, also if you count the number of squares, then it happens to be L times L minus 1. So this is the number of rows in this matrix, HZ or X or HX. Okay, and so by using the formula that I had in the previous slide, which is N minus MX minus MZ, this tells me the number of logical qubits that this code allows me to store. Okay, so this was simple. Now, in order to determine the error correction abilities of this code, here we need to do a bit more work. But it turns out one can prove that the number of errors that you can correct is roughly L over 2. Okay, so notice that this is, in terms of the number of physical qubits, this is square root of n in terms of the number of physical qubits. Yeah, a small thing I wanted to mention here is how does the error correction procedure work for these CSS codes, and in particular for the surface code. So it's the error correction procedure works the same as what I showed for this repetition code. Remember, we had these 3 steps where we measure the syndromes, and then we have this decoding algorithm, and then we undo the error. So here, but I have to tell you what the syndrome measurements are for such a CSS code, which is given by HX and HZ. And so actually this happens to be quite simple. It's just given by the rows of HX. So I look at, let's say, for example, I look at the first row of HX. And what I will do is I will measure the parity of this qubit with this qubit, with this qubit, with this qubit. Yeah, I will measure the parity of these 4 qubits. Okay, and this will give me this syndrome. And I do this for each one of these rows of HX and HZ. Okay, I get an SX and an SZ, and then I have a decoding algorithm that will give me that will try to infer what the error was. Okay, and then I undo the error. So let me mention some of the advantages of the surface code. So one important advantage is that when I do the syndrome measurement, right? So I have to measure the parity of, for example, let's say these 4 qubits, right? So I have to measure the parity of these 4 qubits. And so these 4 qubits happen to be very close to each other geometrically, physically, right? So and so this makes it much simpler to implement such an operation. Okay, another very important advantage is that actually, even though this code can correct up to square root n arbitrary errors on square root n qubits, and if you go above, there are some errors that it cannot correct, but it actually corrects most of the errors, even above that act even on more than square root n qubits. So in particular, it goes up to a linear number of qubits. Another thing is that we actually have an efficient decoding algorithm. So this mapping from the syndromes to an error, there is an efficient classical algorithm that does that. Okay,
so there's a request for clarification regarding how HZ and HX entries are determined from the graph.
Okay, yes. So HZ, so the way HZ is determined is I look at each one of the squares of this grid. Okay, so I have all of these, I take each one of these squares. Okay, so and remember that the physical qubits are labeled by edges. Okay, so if I take a given square, okay, and look at the neighboring edges. Okay, if I'm inside the grid, then there will be 4 edges. Okay, and so in HZ, the rows of HZ are going to be labeled by these squares. Okay, so for example, for this square, I will have 1 row. Okay, imagine it's the first row. Okay. And where will I put 1s and where will I put 0s? I will put a 1 for the qubits that correspond to edges which are neighboring to this square, right? So so here I have 4 of them, so that's why I have 4 1s, and for all the remaining ones I put a 0. So for example, for the row corresponding to this square, I will put a 0 I will put a 1 on the neighboring edges and 0 for all the other edges of the grid. Okay, I hope this clarifies, and I do the same for HZ, except that instead of the squares, I look at these crosses. Okay, so I hope this clarified a bit of the construction. So let me mention now the last important and probably the main even advantage of the surface codes. The main important property is that actually these syndrome measurements, they act on a small number of qubits. So this is of course very related to the first point, but I wanted to make it separately, is that each when I do this measurement, I take the parity, I consider the parity of a constant number of qubits. So 4 if I'm inside and 3 if I'm on the border. Okay, and so in terms of the matrices, HX and HZ, this means that these matrices are sparse. Actually, this is what one calls low-density parity-check codes, or LDPC codes. And this is a property which is very important for fault tolerance. Okay, so on the other hand, and I will talk about LDPC codes. Maybe I'll have to skip it, but in the next few slides. So let me just briefly mention one main disadvantage of this code is that it only encodes 1 qubit of information. Right. So you see, I have this more than 100 physical qubits here, but it only encodes 1 qubit of logical information. So if I have a circuit that I would like to encode using this surface codes, then I will actually need to have 1 such surface code for every qubit of my circuit. Okay, and this is what leads to these very large overheads. Okay, and this is what motivates these LDPC codes. Okay, so yeah, I guess I'm running out of time, so I won't. I will skip this part. So yeah, as I said, LDPC codes, it's the LDPC property is a very important property for fault tolerance, and in particular, it's because of this syndrome measurement step, right? So if I don't have the LDPC property, then basically my syndrome measurements will really contain a lot of noise, and they will give me no information on the error. Okay, so yeah, so constructing quantum LDPC codes with good properties is not very easy, in particular because of this orthogonality condition. Okay, but I won't discuss this. So there are several constructions, and recently there were several breakthroughs in this direction. I wanted to briefly mention what the hypergraph product construction is. It has a nice interpretation, but I will skip it. Also, these LDPC codes can be used for fault tolerance in order to improve the memory overhead. So instead of using these surface codes or the concatenated codes where you encode each qubit within a surface code, in using these more general LDPC codes, which encode more qubits, which don't just encode 1 qubit in a block, but they encode a linear number of qubits in a block. One can get memory overhead, which is a constant instead of this polylog factor. Okay, at least asymptotically. Okay, so let me conclude. Yeah, let me first start with a summary. So we saw that quantum error correcting codes do exist. And we also saw that I can obtain a quantum error correcting code by combining a classical code for X errors and Z errors. We saw very briefly, but that for fault tolerance, the LDPC property is important. And something I didn't mention at all, but I can mention it now, is that these many constructions of these LDPC codes can be seen as well-chosen products of some classical codes. Okay, so this hypergraph product and even more general codes. Okay, briefly mention some of the challenges in this area. Of course, designing LDPC codes with better and better properties in terms of correcting errors, in terms of rates, also in terms of decoding algorithms. This is quite important because you want to do it very fast before the quantum errors propagate. Another thing is that I didn't talk in much detail about what the specific noise model is, but depending on the hardware, you might have a noise model where, for example, X errors are more likely than Z errors, or vice versa. And designing good codes that are adapted to this is a very interesting research direction. Another research direction, which is more related to fault tolerance, is to give good fault tolerance and efficient fault tolerant constructions for LDPC codes. Okay, so let me stop here. I included some starting points for some references for those who want to read more about it. And let me stop here. Thank you.
Thank you very much. I'll just now share the question slides on my end.
So I stop sharing.
So we'll just go through them one by one. So since you finished on just some of the research topics, many of the students in the summer school also kind of get exposure to, rather than kind of, formal theoretical foundations, an introduction to quantum computing while playing around in Qiskit with many of the quantum algorithms that have been known for quite a while. I was wondering what are kind of reasonable projects that such students get started on by playing around with these computational kind of simulations and quantum models that are available online via Qiskit or via other kind of quantum startups. Are there interesting projects, research questions that they could pursue by tinkering around and playing around programmatically in these frameworks?
Yeah, so I think, yeah, there could be interesting projects. I don't know if they're research projects, but just I think maybe it's interesting to see that actually by using an error correcting code, trying to apply a simple algorithm to it, that you indeed get better answers. I think this could be a small project to get into error correction and fault-tolerant quantum computation. This could be a simple project, and to start getting into this. Yes, I don't know if this is the thing you had in mind, but yeah, this is the kind of, like, if you want a project to play with these codes, I would say that this is the simplest, is to take a simple algorithm and to try to run it on encoded data, and to see what it gives. And actually, no, I think there could be some interesting results of this, to try variants of different codes and different decoding procedures on a small number of qubits. There might be various optimizations you can do that can be actually quite helpful. And so I would suggest this maybe. So do you want me to read the questions, or you read them?
Sorry, I didn't realize I had muted myself while you were answering. I can read the questions.
Yeah.
So this is a question that came up earlier during the talk when you introduced the error correction model with the bit flip. So what ensures that the added correction gate has no noise? And if that can be achieved, why don't we just replace that noisy gate with the one we're using for correcting the error?
Not replace the noisy gate with yes, so actually that's a very good question, but that gets into the setting of fault tolerance, right? So the setting of error correction is very clean because we consider the encoding and the decoding as error-free completely. Okay, but this is, of course, this is an idealization, which will not be true in practice. And now, if the error correction part has errors, which will be the case in practice, then you need a more complicated analysis. And actually, this is exactly why LDPC codes are important, right? Or at least one part, because if you don't have LDPC codes, even the syndrome measurements, remember the syndrome that you obtain in order to say something about the error, it's very difficult to do them in a way that in a way in which you can control the noise, right? If the rows of HX have a very large weight, then it's very difficult to compute this parity of all these corresponding qubits. Whereas if it acts on a small number, you can control the error. Okay, so yeah, let me stop here for this question.
Sure. I'll take this third question first then, because we were talking about LDPC. So why are quantum LDPC codes not used as candidate in quantum computation? What is the problem in this field for these codes moving from USA?
So I guess when you, so I mean, the toric code is a valid LDPC code. So I guess here what you mean is these more general kinds of LDPC codes. So there are maybe the main reason is that, so for these LDPC codes which have a higher rate, even though it's LDPC in the sense that the syndrome measurements, they only do a parity of a small number of qubits. These small number of qubits are not located in the same place. They are located across, they're very far from each other. And so this is much more difficult to implement in practice, at least for now. But I believe that in the future, this might be doable. So I believe that in the future, quantum LDPC codes hopefully will play a role in quantum computation.
And this relates to current implementations. So lots of time when we talk about recent implementations, we hear this notion of error mitigation rather than error correction. And so what are the key differences in the two kind of models for mitigation versus correction, and whether there is a formal framework for error mitigation as well?
So error mitigation is more of it's a different framework in the sense that you don't really encode your computation, right? But rather what you typically do is you run the circuit several times. So you take the same circuit, exactly. You take the ideal circuit, you don't try to encode it, and you run it several times. And from these different runs, you do classical post-processing in order to try to eliminate the errors that occurred. Yeah, I'm not an expert in error mitigation, so I don't know if there's a theory behind it. I know there are many papers about it, and there are various techniques that seem to work quite well. I don't know if it reached the level of a full theory.
Do you expect as the experiments scale up, there would be kind of a combination of error mitigation and error correction techniques, or is it really something?
I guess naturally, yeah. Yes, it might be that in the middle range, it might be that one does a combination of both. Yes, I think this is likely.
Yeah. Nayana from India asks, what are the best quantum error correction codes for continuous variable quantum key distribution?
So I think for this is a bit different, but for key distribution, actually it's classical codes that you use, not quantum codes. So this really depends on your protocol. So I can't really answer this question.
The other problems then become slightly more generic. So I'll kind of summarize them in two. One is like, what do you expect quantum computing will look like after 50 years?
Difficult question. I think nobody knows, but I mean, yeah, there is on the optimistic side, we have that we'll have really large quantum computers that can do various quantum simulations, and even maybe more like combinatorial optimization, various optimization problems much faster. And there will be many of these throughout the world that people will be able to access. I think this is possible in 50 years. And I would say it's maybe even likely. But of course, there is, you can go on the pessimistic side, is to say that actually we'll never go much larger than what we have. Maybe we'll get to 100 qubits, but the noise will keep increasing as we increase the number of qubits, and we'll never be able to run a reliable computation. So we'll be limited with these NISQ applications. With limited applications. So yeah, in between these two, I don't know what will happen. I think if we don't try, we will never know. So So we have to keep working on it and hope that it will be on the optimistic side.
I guess, would you want to add anything to kind of the last question over here in terms of, do you expect quantum computing will kind of keep growing in its current pace, or do you expect that there will be a quantum winter in the next 50 years before it kind of really gets to practical large-scale quantum devices?
So yeah, I think it will keep growing, at least in the next 5 to 10 years. And then I think whether after that, it will really depend on the quantum hardware people, the physicists, whether in this time frame they were able to really improve their hardware in order to have a bit more applications of quantum computers. So I think in the next 5 to 10 years, yes, it will keep quantum computing will keep developing, but and then after 5 to 10 years, I would say it will depend on what the results are. By then, yeah, there might be and depending on that, it might explode even further, or there might be a winter.
So there's a request from the audience to ask a question using audio. So I'll let Gaurav go ahead.
Hi, Omar. Can you hear me?
Yes, I can hear you. Yes.
Yeah. So I have a couple of questions. One of them is non-technical and two are a little bit technical. Can you go to page number 12 of your slide?
So shall I reshare?
Yeah, please.
So Gibran, yeah, so I reshare. Okay, so let's do that. So you said 12?
Yeah, page number 12.
Yes. Mm-hmm.
So first of all, I'll start with the non-technical part, which is the disadvantage. So you said that this whole code that you showed, it just encodes 1 qubit. Now, if we are using these many qubits to encode just 1 qubit, then isn't it very inefficient? Or am I missing something here?
Yeah, it is inefficient in terms of storage, of course, because we're using much more qubits than the qubits we need for the circuit. And actually, but on the other hand, what you have gained is that now the probability of a logical error has decreased significantly. So, for example, this is what I mentioned at some point in my talk, is that so if you don't encode, right? So imagine that you don't encode at all. Then, and imagine that your hardware is such that it makes an error with probability P, okay? So
right.
if you don't encode at all, then each one of your qubits will have an error with probability P, okay?
Yeah.
But now if you use, for example, this surface code and encode your qubit into this very large block, then the probability of a logical error, so in the sense that the information which is encoded inside has an error, will actually be exponentially small in the number of qubits here in n.
I see.
So you do gain something. So, and that's why we need to make these. Basically, I can say here. So you need to make this code large enough so that the error will be exponentially small in n. Let's say c to the n, in such a way that you need to take n so that the c to the n is much smaller than 1 over the number of gates that you apply, the number of components of your circuit, so that globally you don't have an error. Roughly, this is what goes on.
I see. Just a follow-up of this, then what about multi-qubit case? Because if we need these many qubits just to encode 1 qubit, then is there a particular formula, I mean, to know how many qubits we might need for, let's say, 2 qubits, to encode 2 qubits or 3 qubits or n qubits for that matter?
So with this method, it will be just n times the number of qubits. So because you'll take each one of your qubits and you'll use one surface code. But for the LDPC codes that I didn't get the chance to talk about much, the advantage is that you would take, let's say, you would encode 1 over 10 times n, like n over 10 qubits, into n qubits, and still get an error probability which is exponentially small in n.
I see. Okay. I have 2 more questions now, coming to the technical questions. So first of all, this graph that you're showing us, I'm sorry, this is the first time I'm being introduced to surface code, so my questions might be very lame or stupid. Please don't mind that. So this graph that we are seeing, the first graph, is this a physical layout of qubits, or is it's just some theoretical construction? Because you're saying that, for example, the blue square, you're saying that these are the physical qubits which are very near to each other. So how do I look at this this matrix structure that you have shown, or the graph that you have shown?
So two things. So, I mean, there is the completely abstract point of view. If you're a mathematician or a computer scientist, then you don't need to picture that you have physical qubits that are close to each other. You can think of it as just a way of representing, a graphical way of representing hx and hz. Okay, so it doesn't play a particular role. But in practice, of course, when you would want to implement this, you would really put it on a grid, right? So, and that's why, for example, if you look at the Google platform, it's exactly put on a grid for this reason, so that when they scale up, then they actually use it directly to be able to encode information in the surface code, right? And then you would really put the qubits. So this qubit and this qubit would really be close to each other physically.
Right. Okay. So one last question. How do you then decide the position of hz and hx? Like, for example, here you have chosen a particular third row, third column for hz, and then at some place we have hx. How do we decide
Okay.
these positions?
So maybe I didn't explain it well. So what I mean is that I actually, for each such square, I have a row in my matrix. It was a bit fast maybe. So I do that. This was just an example. So it's not that this is hx. It's just, so I consider my grid here. I take every single square. So I can do them in order. I can take, for example, this first square. So this first square gives me a row in my hz, and this row will have a 1 on this edge, and this edge. Okay, and I add a row with these 3 ones. Okay.
Oh, I see. Okay. I see. Okay. So it's so the first row of hz is not the hz that is drawn. That's why. Okay. I get it now. Yeah. Perfect.
Yeah.
Okay. All right. Okay. Yeah. Thank you. I'm done with my questions. And thank you, Omar. It was a very nice talk. Thank you so much. Yeah.
I think there are any other questions online. So let me thank you, Omar, again. It was a wonderful talk, and it was wonderful kind of listening to it. Thank you to the audience members, and hopefully we will see everyone again tomorrow for our talk with Nathan V1 Quantum Machine Learning. Thank you. Goodbye.